on 4 refereed published papers, of which I have copies here, and I submitted it for a colloquium at the physics department at the University of Virginia. It was accepted until I sent them a copy of the PowerPoint slide presentation a week before. I got an email saying that my colloquium was canceled because of unknown, unspecified objections by an unspecified number and unnamed faculty members of the physics department. So I'll leave it up to you to see how many outrageous things I say in this particular talk.
I'll make notes.
Start out with, I spent my entire career in nuclear engineering, specializing in reactor physics. For me, physics was the physics of the nucleus. Neutrons come out, protons from accelerators, we hit things, we make stuff. My physics was taught by Robley Evans from the book The Atomic Nucleus, and he was personally in the classroom. The experiments were taught by Norman Rasmussen, who ended up being an NRC commissioner and wrote the book on reactor safety. I was fascinated by a number of things, including the magic numbers as applied to nuclei and the semi-empirical binding energy formula, so much so that we tried to put together a semi-empirical horse betting formula, but that didn't work very well. And I was always disturbed by some concepts, and one of those was the idea that the neutrons and protons in the nucleus were racing around inside the nucleus, even though there was hardly any room in there for them to race. The other thing that bothered me was the idea that an alpha emission would occur because the alpha particle somehow or other got a certain amount of energy and it ran as hard as it could and it hit the potential barrier. Sometimes it bounced back, and every once in a while it magically got through by tunneling, and that was it. And a lot of the theoretical mathematics that went with all of this never penetrated me. Maybe that's good. Engineers are different from scientists. We have to solve real problems. We get fined or fired for making mistakes. My field was highly regulated, and we had to prove everything by experiment, and we were not allowed to ever use a theory or a calculation that wasn't verified in the range in which it was going to be used. Which means that engineers are always second guessing. What did I forget? What did I do wrong? And check everything. Codes, theory, everything has to get checked, and gets checked over and over and over again. I met Dr. Lucas at the meeting in Tulsa, and he brought out the idea that nucleons are charge-carrying ring magnets. Well, nobody can look close enough to tell whether that's what it is or not, but to me, if it behaves like it, that's fine. Bothered me a little bit that a ring magnet is thin, and to me, a nucleon is more of a spherical. At least it seems to bump things in all directions. But anyway, that's fine. But the real key to the whole thing is he puts the nucleons in fixed static shells inside the nucleus under force balance. And the idea is they aren't really moving at all. They're sitting there, at most vibrating. But they're not racing around at I don't know how many kilometers per second. And the thing that totally amazed me is with this idea of static shells, he explained the magic numbers and came up with a new and better semi-empirical binding energy formula. I'll show you the old one. And those are two of the things that I was really, really, really interested in for all those years. So we put together a paper for Nuclear Science and Engineering, which is my journal, and it ended up being published as a letter to the editor, but it gives the nuclear model and the semi-empirical binding energy formula. I sent a copy of that to Professor Hans Weber in our physics department at the university, and he said, well, nobody will believe your ideas unless you apply them to something new and different. And why don't you apply them to the super heavy nuclei? Which is fine, except I didn't have the foggiest idea what a super heavy nucleus was. So what do people do these days if you don't know something? You go to Google and you put in the words and you see what pops out. And what popped out was a summary paper by Professor Mohini Gupta in India, who not only gave the experimental data but also the theoretical comparisons. And so I got in contact with Professor Gupta and I started to do some work. And this is what happened. Well, the initial work turned into a paper, and Gupta suggested it be submitted to the Annals of Nuclear Energy, and this is a copy of the paper, one of the papers. And it was published in August of 2011. Published a second paper. I figured, well, if it works for these heavy nuclei, maybe it works for the ones further down too. And of course, I used the Bible, which is the table of isotopes. When I was a professor, the whole thing was about ½ an inch thick. Now it's 2 volumes, and this is only one of the 2, and this is not the latest. So, I published myself 2 papers in the Annals of Nuclear Energy on magic numbers, and then we put together as a joint paper with Dr. Lucas and Dr. Ed Boudreau and Eric Baxter. We put together a paper for physics essays, and that was published last year. And there's some new work in here. I have been in contact with some scientists at Dubna in the Soviet Union, or what do you call it, Russia now? And they are working on what they call non-traditional magic numbers, like 6. And there's new information on the magic number 58, so that's part of this talk as well. I don't have to say a lot about this, but I will start showing a little bit about what was in the 1950s nuclear physics for engineers, a little bit about the electromagnetic model, super heavy nuclei, and then a bit about some of the isotopes and how they fit to all the data in these big heavy tomes. The original physics was heavy on experimental data, which is the way it ought to be, and analysis of what the data implied, what wasn't yet proven, but it was not cut in stone in the sense that Evans said that if a better theory comes along, we'll change. And that's unfortunate. We don't do enough of that to change. It had potential wells, barriers, wave mechanics, what all those things meant. But it was an orderly treatment, chapter by chapter, charge, size of nuclei, mass, moments, isotopes, systematics, forces, decay, everything under the sun, to the best of what they knew in the 50s. And here's what we knew. The magic numbers 2, 8, 28, 50, 82, and 126 are magic, closed shells of some kind, and lead to extra stable nuclei. And the best example is the alpha particle, is doubly magic. A very, very tightly bound particle. Oxygen 16, doubly magic. It's indestructible in nuclear reactors. It's the basis of all our fuels, the oxygen oxide part. The double hump fission yield curves are based on a light fragment and a heavy fragment. I've changed which fragments they are now, but this was what was thought in those days. But the magic numbers were responsible for having delayed neutrons, and delayed neutrons changed the time scale of reactors from microseconds to seconds, which means we can control them with people putting a finger on a button, unless we get to that place where we outrun those delayed neutrons, in which case we call it a bomb. Finally, the poisons, for example, xenon-135 is one short of doubly magic, and it's got a 3 million barn cross-section, one of the heaviest cross-sections known, and it is the reason why the first atomic pile shut itself down, because the xenon built in negative reactivity absorbed too many neutrons, it shut itself down, and if Fermi hadn't had space for a few extra fuel elements, they wouldn't have been able to go critical again at Chicago. So, and finally, lead-208 is the last stable isotope in the table in this nice graph going up. Everything heavier than lead-208 is radioactive. Here is what was known, the stable isotope data. Not very many isotopes there, but what you see are a couple of things. You see a bunch of peaks down here, and that low peak is your alpha particle, very tightly bound. This is binding energy for A versus mass number. The general nature of the whole curve is that anything down here is possible to have fusion and make energy. Anything way up here is fissionable at the high end, spontaneous fission, but pretty much alpha decay all the way back. And right down here in the middle at iron, that's where a star runs out of gas, and you have a supernova if there's enough mass, it can do nothing but collapse. And that was explained by the original semi-empirical binding energy formula, and you can see that it missed all that structure down at the bottom end, but it was explained in the following way, that every neutron or proton attracts every other one, so that's proportional to the volume or number of nucleons. So that's such a basic value. Then you have to subtract something for the fact that these are short-range forces, and you have nucleons at the surface that don't have a neighbor, so you take those away. Then you have the Coulomb energy of the positive particles trying to blow the thing apart. And finally, you have an asymmetry part, which says it's bad to have too many neutrons or too many protons. Unfortunately, the asymmetry term in that equation was symmetric, because it was n minus z squared. So some of it was done well, some of it was not done so well. But what came out of that asymmetry term are the mass parabolas. And I always like these. It shows that if you've got too many neutrons, you have beta decay down to a stable valley. If you've got too many protons, you have positron or electron capture decay also to go to stability. And for an even nucleus, it's a double parabola, and you go ping pong from one side to the other. And this gives you the interesting case of a double beta emitter where this isotope, rhodium-45, can decay either by beta minus or beta plus with a split. So what's the nature of the closed shells? Well, what makes liquid drop model that the idea that fission occurs and the nucleus is able to slosh back and forth. Why doesn't the semi-empirical binding energy formula match the low peaks? And what's the physical decay mechanism? So these are things that we've tried to answer in a more modern sense. with Dr. Lucas's model, protons and neutrons occupy fixed positions in symmetric 3D space under static force balance. They're distributed in 6 double cycles. He has 8 cycles, but I reduced it to 6 because I didn't think that any more than 6 were ever used at any one time. And the occupancies are 2, 8, 18, 18, 32, and 50 for the 6 available shells. And then because I only use 6, I've adopted the idea that an inner shell can expand to the next number at some point, just like the rare earth series is an inner electron shell that changes its occupancy, and that's why you go through, I don't know how many isotopes, with almost all have the same chemical properties, but different mass numbers. And so now we finally get to some of the data. This is from a Lucas paper, but he didn't do the data, but it shows that the nuclear density for, as a nucleus gets heavier, it thins out in the center. And that says that not only are they distributed in static positions, but they tend to be more of them to the outside than the inside. And this is the model for lead-208. The 2 blue shells are the proton shells of 50 and 32. And they occupy the outside because they're positively charged, and on average they want to get as far away from each other as they can. So they don't want to put a few in the middle because that would be more total repulsion than if they're all on the outside. And then the neutron shells, which here are shown as electron-proton combinations, but I call them neutrons, and I call them polarized with a plus n and a minus n. And they occupy 5 shells going in of 50, 32, 18, 18, and 8, getting to 126 with the center empty. These are some of the doubly magic nuclei and how the shells would be filled. And the only thing I'll point out to you is that you can get 20 by either 6 and 14 or 18 and 2, and I think it depends on whether you're talking about protons or neutrons as to which of those combinations is actually used. But I don't think that neutrons and protons are alike. Protons like to be in the outside, and I think you can get to some non-traditional magic numbers like 6, which is what the people at Dubna are working on. So the magic numbers are composites of shells, and if you have a shell that's turned sideways, that might be the slippery part that allows the 2 halves to slide and decouple. But I believe that the neutrons polarize inside, and they polarize with their plus ends toward the center to get as far away from the protons as possible. And I think the most important conclusion on here is decay is a vibration process. They basically sit there, and what most they can do is vibrate, so they vibrate. Force laws are nonlinear because there's lots of different ways that you can vibrate. I've added that a neutron or a proton, when bumped, vibrates internally, and that's the basis of beta decay or positron decay. The individual nucleon just comes apart if excited sufficiently. And you can have a variety of rotations and groupings. But I did do a mathematical model saying that if all the forces are springs, what you get is a classical vibration equation from F equals ma, which is the analog of the Schrodinger wave equation. So I believe that vibration acts like wave mechanics. Semi-empirical binding energy formula, the new one is basically better because it, instead of just saying that I have so many nucleons in the nucleus, and that's one of my terms, now it depends on where they are, which shell they are, as to how you count them. And so now they are counted correctly rather than the old way, and the asymmetry is actually ends up being asymmetric. And what you get is a new semi-empirical binding energy formula, which is now fitting 3,000 nuclei instead of a few hundred. And if you will notice, you're getting all of these peaks in here, and the only thing wrong with it that I can see is the alpha particle peaks at 8, and the actual data is 7, but this is a fit to the data, so what do you say? At least it's got the structure built in. This is the work that was done in conjunction with Boudreau and Baxter. Baxter wrote a computer program that will give you iteratively find a minimum energy position. And what you do is you take a nucleus and you give it a guess as to where the neutrons and protons are, and then you let it iterate to a final position. And for the nuclei that they were able to do, they actually came up with quantitatively comparable decay energies. So you basically show that if you put these nucleons in the right place, you get the right energy. And to me, some of the things that come out of this are utterly fantastic. Now, what about the super heavy nuclei, which is the challenge from my physics professor friend? You make them by taking something like calcium-48, which is a heavy doubly magic nucleus. You get a big accelerator and you shoot those particles at things like plutonium and californium and berkelium, and you see what you make. And they have made a potload of new nuclei. The work is being done in Germany, Russia, Japan, and the US. The longest half-lives are 12 minutes and 22 seconds, so they're pretty short-lived. At one time, when I was younger, it was thought that if you went up, there might be an area at much heavier where you had extreme long stability. That's not the case. The higher you go, the harder it is to hold the nucleus together. And this is what the super heavy nuclei data look like. This is a plot of neutron number against proton number, and the stable nuclei end right there, and then the things that you've been able to make are up here. And the first thing that struck me is I can draw a straight line of constant slope through that data. And the straight line has a slope of 1.54. So for these heavy nuclei, you want 1.54 neutrons for every proton on average. That's where you have the longest stability. The red is long-lived, the black is stable, and so this is an indication of the data. Now, the data aren't very good up here. They're still making new data and getting better statistics, but it's interesting. And what I did is I kind of said, well, let's find upper and lower bounds to ends and tops and bottoms and the center and so on, and see what you get out of that. And you'll have to take my word that I more or less did it right. The lower end of the red peninsula is near 90, Z90 and N140. Upper end is near 100 and 158. The low end of the green is 82, upper end around 108. The shoal is near 108, lies between 158 and 164. The island is near 108 and 182, and then it lies between 102, 118, 172, 184. The reds are all proton numbers, the whites are all neutron numbers, and what you see is the same numbers coming out over and over: 140, 158, 164, 172, 182, 184. The red one's 90, 100, 82, 90, 100, 108, 102, 108. 118. Pretty much that's the top end right now. They're hoping to have get 120, but 118 is as far as they can verify. Gupta had cited 3 theoretical papers, and the theoretical papers seem to have found that with all sorts of weird distorted nuclei and so on, about 8 magic numbers, and it seems like 7 of them agree with just the rough bounds of these of the data. 114 doesn't match at all, and I don't think it's right. But the thing that struck me about it is, hey, we've got lots of magic numbers, not just a few, a lot of them, and they're not very far apart from each other. So can we verify which ones are new and find out and see what you get out of that? So I started playing games. This is higher mathematics. There are plus signs in there. What can you get if you take the 6 shells and play with the numbers that are known? Well, you add 8 to the 50 and 32, and you get 90. Add 2 more, and you get 92. I call this maybe semi-magic, magic plus an extra pair. But if you take 18, add it to 50, 32, you get the 100. Add 2 more, 102. Add 8 to the 18, you get 108. Add 2 more, you get 110. 2 18s and 118. 2 18s and 2, 120. Those are all the numbers that I just showed you, theoretical and otherwise, that match the experimental data. If that works, hey, let's try it for neutrons, except now I have to play the game of letting a shell fill to a higher level. So if you let one of the 18s go to 32, you get 140. If you let let's see, how did I do this? Oh, add 2. If you let one of the 32s go to 50, then you get 158. Let the other 18 go to 32, you get 164, and you see I end up pretty much agreeing with all the other magic numbers that were suggested from the data. So it seems to cover a goodly share of what you see. So now it's time to think a little bit more, and if that worked for neutrons, well, if it worked for protons, you can use it for neutrons as well. So you tack on some more neutron numbers. And then I found a very old paper by Linus Pauling in 1981, and he suggested some numbers down lower, like 58. And you get 58 by adding 8 to the 3218. And if you change that to 18, you get 68, and one more 76. So there's a couple of additional ones to check in the upper end. This was, Pauling had an idea of a parameter that he called a spherical radius, and the various peaks for a series of isotopes are what he used to verify the 58 and the other numbers. So I went through this gigantic book and went through actually more than 8 isotopes, but I'll just give you a little bit of the flavor of all of that. There are 19 isotopes of thorium. I never thought there were that many. And Gupta, in his paper, said that the next doubly magic number, nucleus, would be the holy grail of contemporary physics. Well, the holy grail is thorium. Specifically thorium-230 and 232, which are very long lived isotopes. And it just so happens that not only are they doubly magic, but they're sitting on the optimum N/Z ratio of 1.54. Uranium has got 20 isotopes, and 2 of them are doubly magic, and that tends to explain fairly long lives going down towards lighter isotopes. But the ones that we use, 236 and 238, are also pretty long-lived, and they are more or less stabilized by being very close to that N over Z ratio, right down in the middle of. There is something I should mention, the Seaborg criterion for spontaneous fission. And I'll show you what that does. Fermium 100 would be one of my new magic numbers. And the longest life isotope of that is 1 short of doubly magic, fermium 257. 258 is doubly magic, but it decays by spontaneous fission. All the other half-lives, lighter or heavier, are short. And the reason that the odd one is the longest life is the Seaborg criterion, which basically says that that nucleus is slightly asymmetric, and therefore it cannot vibrate in all degrees of freedom. So that restriction is what makes it live longer than the others. If you don't believe that one, try nobelium, and you get exactly the same behavior. The longest life existing isotope is 1 short of doubly magic. Went down to cerium. There's 20 isotopes. The doubly magic one is almost 90% of the natural isotope. But having doubly magic tends to give you heavy end isotopes with reasonable lives and light end isotopes with reasonable half-lives. I ran across this data as a result of talking to the Russians, and it shows that cerium has a kink at 158, so that's additional information that says 58 is magic. Well, I won't go through all the details. Dysprosium has some of similar behavior. You tend to have longer lives, and the bounds of existing isotopes with reasonable lives are influenced by the magic. Osmium, lead. The only difference for lead is I would add lead 210 as being stabilized by having that extra pairing. Now, new information, double hump fission curves. If you put 58 in the light fragment instead of 50, what you get is almost perfect agreement with the experimental data, at least for uranium. Slightly off on some boundaries, but pretty much says that 58 is a magic number. That explains your double hump fission curves. And now this is some information from the Russians. They have something called a kink radius, and here for at least 5 isotopes you confirm 82. But what you also see is for a couple of isotopes you can confirm 68. Here's another set of their curves, and here again for about 5 isotopes you're confirming 58, and surprisingly enough you're confirming 50 as well with his model. I'm almost finished. Maybe it's. Oh, I'm not doing that badly. These are some of my newer ideas. I believe that the intrinsic mass of a nucleon, like a neutron photon, is about 99% of the mass, and then there is the rest of it is tied up in the EM fields between nucleons, inside the nucleons, and I believe that beta decay is due to internal vibration of a nucleon. These are essentially new ideas. They're not in any of the theoretical models, but I believe you have to have an explanation for why do you get beta decay as well as why do you get alpha decay and fission. So I consider that vibration is the basis of all decay, and the data appear to be quantized because of the fixed amount of energy between the configurations that are allowed in the models, and you get an almost continuous mass distribution out of it. No barrier penetration for alpha decay. The alpha particle just blows away. We don't need wave mechanics. Always bothered me in the physics book, the deuteron wave function, instead of looking like other wave functions, is weird. And I've tried I don't know how many times to understand it, and I don't believe the information for deuterium, or the deuteron. But the Schrodinger equation is a perturbation analog to vibration, and so I think vibration is really what's happening. Where am I? Magic affects number of stable isotopes and sizes, the extent of isotopes, and the half-lives. And the ones near 1.54 ratio are the most stable, and the heavy ones won't, by definition, won't be short-lived. You're not going to find a ring up much higher that's got. And so the table of isotopes is now 4.5 inches thick. This is half of it. And I believe that there's a new one coming out that's even bigger. And I'm willing to bet that it has not been examined for all the possible systematic behavior that you can show if you just start to suspect that there is systematic behavior to look at. So I think that that's where research ought to go. And that ends this one. I'll take questions or start the second one, but I need a drink of water. Is this available?
It's on you.
I had to try once, just seeing, I didn't realise this, I didn't think about this protons wanting to go out to the outside, trying to get the structure for the magic numbers, and so I tried that and it didn't work. And then later on I worked out that I predicted a particle that's 1/27th the mass of a proton, and there has been found at Carmen. And so I decided to see whether or not those would work. And I just varied all the different numbers I tried to see if a proton and a neutron were made of some other number of a smaller thing, one would work. And it turns out 27 is the best. And it does give just a thing full, closing shells. Well, that does work reasonably well for getting the magic numbers.
Well, I'm old-fashioned in the sense that I grew up with neutrons and protons, and I've seen with my detectors neutrons coming out of things.
Yeah.
And so I believe they exist, and they're the building blocks.
Yeah.
And I don't feel the need to take them apart into smaller.
But people talk about this liquid model, so it's sort of going away towards that, having 27 bits in it. 27 makes a 3 by 3 by 3, nice little thing when it comes loose. Yeah, I know. Well, it's a nice coincidence, and it fits both things.
Again, the nucleus is so packed that it's got to behave like something like fixed positions.
Mm-hmm.
And why anybody taught us that these things are racing around like crazy inside, I don't know why. I don't know why I ever believed it. But I've spent enough years thinking about some of these things to have decided that I disagree with some of the things that were in the book, and I think there are better explanations. And I think I found some of them. Now, maybe it's a little while to find it by just using arithmetic, and not only arithmetic, but just plus signs.
So one of you is wrong, and nobody knows why.
What?
Is one of you wrong because of the disagreement?
Is who wrong?
One of you, I don't know. Either you or him. I mean,
I don't know that we're disagreeing with each other. He just said there might be a different way to make the particles, and I don't see a need for anything more than neutrons and protons. I do see a need for how do you put them in, and what keeps them where they are, and how do you explain decay when it occurs and why it occurs. I think that all comes out of this. At least I'm not sitting here trying to find another new model. I don't know how to switch this to the next talk.
Who's the next one?
I'm the next talk.
I know.
I'll come up with this for you.